this is Mr. Roberts, and this is a look at the study team test from Chapter 5. Question number 1 gives us a sequence that has a first term of -10, a second term of -3, and a third term of 4, +4, and we're asked to write the next 4 terms of the sequence. The two sequences that we've been looking at in this chapter primarily are arithmetic and geometric. Of course, there have been other ones, some that are best written down using not explicit rules, but recursive definitions, for example, the Fibonacci sequence, and some quadratic sequences that we've looked at. So if I'm looking at this particular sequence, I do not have a common ratio, right? The ratio for any sequence is a term divided by the previous term. So for example, if this were a geometric sequence, I could look at -3 over -10. That's the difference between the second term and the first term, and that would have to be the same as the difference with the third term and the second term. And it turns out that +3/10, if I was to simplify this, this is it's 0.3 or 3 over 10. 3/10 is not the same, definitely, as -4/3. So this is most definitely not a geometric sequence. What it does have is a common difference. So if I look at -3 and I subtract the previous term, which is minus a -10, I get a value of 7. And 4, and then subtracting the previous term, -3, ends up being 4 plus 3, which is 7. So this is an arithmetic sequence. I have a common difference of 7. And if I wanted to write the next several terms, I would just leave off at this third term of 4, and then I would add 7, which would give me 11. 11 plus 7 would be 18. 18 plus 7 is 25. 25 plus 7 is 32. So for this sequence, the generator is add, so it's addition, and just add a +7. What kind of sequence is it? How can you tell? Well, the sequence is arithmetic. And I can tell because it has a common difference. The difference between each successive term is 7. Below it says, in the space below, create multiple representations of the sequence, a table, graph, and a rule. And if you'll recall, in a sequence, we of course restrict the domain to just the ordinal numbers or the natural numbers. So I could talk about the first term, the second term, the third, the fourth, the fifth, and the sixth term. And each of these has a value. Turns out the first term was -10. The second term was -3, 4, 11, 18, and the last one there is 25. So again, one of the big ideas with arithmetic and geometric sequences both is that we do restrict our domain to just the natural numbers. If I wanted to come up with a rule for it, you'll notice this is not geometric. I'm using T of n notation here. I could say T of n is, again, my common difference was 7, so each time I would be adding 7. So I would say 7 times n. And again, this is the idea. Repeated addition is shown with multiplication. So each time n increases by 1, I'm adding, or I'm increasing by 7, right? I'm adding an additional 7. And then I would also need to know the 0th term of this sequence. I can see the first term is listed as -10, so the 0th term would be the one right before that. To go to the 0th term, I would subtract an additional 7, and I would get -17. So this is an explicit rule for this particular sequence. It's 7n minus 17. And of course, notice the relationship between this and just a linear function, right? F of x equals mx plus b. So this definitely, these points here will be in a straight line. And then finally, let's come up with our a graph for this sequence. So I've set up 0 so that it's roughly halfway through this graph, and I have down to negative 10 and positive 10. And I decided to set it up this way because the sequence does start with negative numbers. So if I was going to plot these, at 1, the first term is negative 10, so I have this particular value that's part of the sequence. At 2, I jump all the way up to negative 3, which should be right here. At 3, I'm landing at the third term, which is at 4, so that's 1, 2, 3, and 4. And the fourth term, the fourth term is at 11, which would be just off this graph, but I think I can convincingly place a dot right here. So we do notice that these are collinear. They're making a nice line. However, I'm not going to connect them because this is a discrete situation. These sequences, we just have terms and we don't have values in between them. So that's our solution for question number 1.